Hello everyone, I'm Chen. Today I'll be presenting my paper, Visual Acoustic Matching, which was done in collaboration with Rohan, Paul, and Kristen. Let's begin by watching an example of how one drum kit sounds differently in 5 different spaces. Notice how the geometry and the materials of the room affect the sound we hear. Whenever we hear sound, it is always shaped by the space. When sound wave propagates in space, it reflects off, gets absorbed, or transmits through surfaces, and thus acoustics is a function of geometry, materials, source and listener locations. For example, when we see a large music hall, we expect to hear a lot of reverberation, while in a small living room, we would expect to hear less reverberation. What can we do if we understand the acoustics of a space based on visuals? We can alter the acoustic signature of the sound. For example, in augmented reality, when we have a virtual phone call, we want to make the caller's voice to sound like they were speaking in the same room. And for film dubbing, we want the dubbed speech to sound like we're recorded in the filmed space. And for video conferencing, we want to match people's voice to their background image. In this project, we are proposing a novel visual acoustic matching task, the goal of which is to, given a target space specified in an image, to transform a source audio clip to match the acoustics of the target space. There are 2 main challenges. The first one is how to perform cross-model reasoning, and the second one is how to obtain the right data for this task. Our key ideas are first, to reason how image patches affect acoustics with visual attention, and secondly, to leverage web videos with novel self-supervision for learning. We propose an audio-visual transformer for audio generation model, or short as AVATAR. We first extract a sequence of audio-visual features and a sequence of audio features. We then feed both feature sequences into a cross-model encoder to perform cross-model attention reasoning. We then upsample the output sequence to recover the time domain signals. And we also use a multi-resolution speech loss to improve the quality of the speech. Lastly, we perform acoustics alteration if there is no mismatched audio, the goal of which is to create acoustic mismatch by performing the reverberation and acoustic randomization for self-supervision. We experiment with 2 datasets. The first one is sound spaces speech, which is a synthetic dataset constructed on sound spaces, and it is to serve as clean test bed. The second one is acoustic AV speech, which is a web speech video dataset, and we use acoustics alteration strategy to obtain input. In this experiment, we measure the closeness to the ground truth, the correctness of acoustics, and speech quality for the synthesized speech. And we show that our model strongly outperforms traditional and heavily supervised approaches. Here we show how our model can be used to match different environments on AV speech given the same input speech.
Stuff it into you, his belly counsel.
Stuff it into you, his belly counsel. Stuff it into you, his belly counsel. Stuff it into you, his belly counsel.
The reverberation time for these speeches are increasing accordingly, and this indicates that our model learns to inject more reverberation into a speech as the environment gets bigger. Here, in this example, we want to show that our model makes a remote participant sound like he is speaking in the room with us in a virtual phone call.
If a man had stolen a pound in his youth,
please check out our website for more details. Thank you.